class. Oy, oy, oy. Hola, good morning. Wait for a few more people, then I'll get started. Try to make it a short lesson today and get you out of here early, is my hope. All right, I'm going to go ahead and get started. Today we are talking about something called wave superposition. Okay. So wave superposition is when two or more waves combine. All right. So there's something called the principle of superposition. And what that says is if you have two waves, d1 of x and d2 of x. So what do I mean by that? So think about this like f of x, function f of x. The displacement of wave 1 as a function of position and the displacement of wave 2 as a function of position. Then when these two waves overlap, they will combine, and the total displacement at location x is the sum of the first displacement as a function of x plus the second displacement at x. Okay? So that's called the principle of superposition. So what does that mean? Well, what if I have two waves? So I'm going to draw them. So displacement as a function of position. And maybe wave 1 looks like this. And wave 2 looks like maybe like that. Okay? So let me put some numbers on the axes here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So I put some numbers on the axes here. Okay. So we can think about this. It doesn't really matter which one you call wave 1 or wave 2. But what we would do if we want the total wave, it's a lot like adding two functions f of x and g of x, okay, to make a third function. It's exactly like that, okay? So what if I want to figure out what is the total wave here at x equals 0? At x equals 0, both waves are 0. So 0 plus 0 equals 0. So the total wave is going to be equal to 0 there. Now what if I choose, for example, this location? Here I can see that wave 2 is approximately equal to 1, and wave 1 is approximately equal to 2. So 2 plus 1 is 3. So that's going to be the total wave at that location. If I look at this location, wave 1 is approximately equal to 2. Wave 2 is approximately equal to 4. 2 plus 4 is 6. All right. If I look at this location, I can see wave 1 is equal to 0, wave 2 is equal to 3. 0 plus 3 is 3. I'm just picking some random spots here. Here I have wave 1 is equal to roughly -3. Wave 2 is equal to roughly +3. So when I add them, I get 0. Okay. And then here it looks like wave 1 is equal to 0, wave 2 is equal to 3, so I add them up and I get 3. So this is just an example. So what we do is we take a couple of points like I just did. We add up d1 plus d2. So I have sort of a skeleton for what the total wave is going to look like. And then I just connect them with a nice smooth curve. Okay? One of the things we notice here is that, like at this location, the two waves are both positive, and so when we add them together, they create a bigger displacement, okay? So at this location right here, we have what is called constructive interference. The two waves are combining together to make a bigger wave. So how is your ear going to perceive constructive interference? Well, if we make the displacement larger, it's a bigger wave. We know our ears perceive amplitude as volume. So constructive interference of sound waves is perceived as a louder sound. Constructive interference of light waves is perceived as a brighter light. Okay? Here, I can see that one of the waves is positive and the other one is negative. Okay? And so when they combine, you get a positive plus a negative. So it equals something that's closer to 0 when you combine them. And so that would be perceived as either quieter or dimmer. And that is called destructive interference. Okay? All right? Excuse me. Now, destructive interference can be complete or not, or incomplete. All right. If the two waves are equal and opposite, then you would get like 5 plus -5. And so that would equal 0. So you would get complete cancellation of the two waves. So that would be completely destructive interference. if the two waves have opposite signs, but they are not the same size, so you have maybe like a wave that has a displacement of 5 and a wave that has a displacement of -3, then they would combine to make a wave of size 2, which is smaller, but it's not completely canceled out, so that's sort of incompletely destructive interference. Okay, so another thing I want to say about constructive interference is if you had a wave that had a dip and then another wave that has a dip, and you combine them, they make a wave with an extra big dip, and that is still considered constructive interference. Okay, so constructive interference means that both waves are positive or both waves are negative. All right, because if you had two waves of size -3, for example, -3 and -3 is -6, that is still a larger wave. Okay, even though it's a larger wave in the negative direction. Destructive interference, you have the waves have opposite signs, so plus and minus or minus and plus. Okay. So I'm really tired. I don't know what my problem is. Had 2 cups of coffee already and ate breakfast. So what if we have sources at different locations? Sources of waves at different locations. So maybe you have a source right here, and you have a source right here. So I'll call this source S1, and I'll call this source S2. Okay, so these two waves are, or these two are like two speakers, basically, or two flashlights, or something like that. So these are two sources, okay, and I'm going to say that these sources are what is called in phase. Okay, and in phase means that the two waves, or the two sources, are emitting waves at the same time. Okay, so if we think about a wave, it can have a peak and a valley. The technical term is a crest and a trough. So both of these waves are emitting crests at the same time, and they're emitting troughs at the same time. Okay, so they're in sync. The technical term is in phase. Okay, and so as we know, these waves are going out in every direction. These waves are just traveling out into the world. So you can almost think about it like someone dropped 2 stones in a pond, and then you have the ripples headed out from both locations. Okay, and right here we have an observer of those two of the waves. Okay, so the wave comes out and it travels here and it lands at the observer, and this wave travels here and it lands at the observer. Okay, now here's the thing. If we look at it, this distance right here, okay, and this distance are not the same. Okay, so I'll call that R1, and I'll call this R2. These two distances are not the same. So what that means is that even though both of these sources are emitting a crest at the same time, they won't arrive at the observer at the same time, because this crest is going to arrive later than that crest because it's further away. It has further to travel. Okay, so even though the sources are in phase, because there's different distances that the waves travel to get to the observer, when they arrive at the observer, they're no longer in phase. Okay. So that's kind of interesting. All right. So actually, we could have it where these two sources are emitting a crest at the same time, but when they arrive at the observer, a crest arrives at the same time as a trough from the other one, and they cancel each other out. Okay. So there's so basically, the observer might experience constructive or destructive interference. Okay. Even though the two sources are in phase. Now, it's not likely to be complete. If it's destructive, it's not going to be completely destructive because if we think about it, this wave traveled further to the observer, so its amplitude has decreased. As we learned in the last lesson, the further a wave travels, the more its amplitude decreases. So these two waves, once they arrive at the observer, they won't have the same size, and so they can't completely cancel each other out. All right, so there's a thing called the path difference, which is denoted by delta R, and it's equal to R2 minus R1. All right. That's called the path difference. And what we do, if we want to know, if we want to predict whether we have constructive or destructive interference right here, what we do is we look at the path difference and we divide it by the wavelength. All right. Now the path difference is measured in meters, right? Because it's a distance minus a distance. And we're dividing it by a wavelength, which is a distance. Okay, so we have a distance divided by a distance. So when we divide these two, it's unitless. It doesn't have units. So it's just a pure number, like 4. Not 4 meters, but just 4 with no units. And if you find that the path difference divided by a wavelength is equal to an integer, n, so a whole number, then that means that you are going to have constructive interference at that location. Okay. If you find that it is equal to an integer plus 1/2, so for example, and by the way, integers include negative numbers. All right. So -1, -2, -3. Negative whole numbers. If it's an integer plus 1/2, so for example, 0.5, 1.5, 2.5, -3.5, stuff like that, then you are going to have destructive interference. Okay? So basically what we want to do, if we want to predict what kind of interference are we going to have right there, we need to compute this ratio and see whether it's an integer or an integer plus 1/2. Now, what if you get something like you do this ratio and you get, I don't know, 1.75. 1.75 is halfway between 1.5 and 2. So it's like halfway between constructive and destructive, so it's neither constructive or destructive. Okay. If you did this ratio and you got 1.6, 1.6 is closer to 1.5 than it is to 2. So it's kind of like more destructive than it is constructive. So let's do an example. Let's suppose that these are sources are emitting sound waves of frequency 8,500 hertz. Okay. And we'll say that this distance is, let's make it 30.2 meters. And this distance right here is maybe 37.8 meters. All right? And so we want to know, is there constructive or destructive interference at that location? Okay. So first thing I'm going to do is I'm going to compute lambda. So I have this equation V equals lambda F. All right. So that says, dividing both sides by frequency, I get V over frequency equals lambda. So the speed of sound, as I told you in another lesson, I said it's 340. The frequency is 8,500. Hang on, I think a dog is getting into something. Hazel! Hazel, no! What are you doing? No, no, no. You come in here and sit down. Come on. Come on, Hazel. Come on. Come today. Lay down right here. Good baby. You stay in here. She's very sneaky. She's really skilled at figuring out when no one is paying attention to her. And then if people are paying attention to her, she just plays the role of this old granny dog, and she can't hear anything. She just kind of lays around and is really sweet and kind of clueless. And then the moment you stop paying attention to her, she goes into action, and she is actually really smart and does all kinds of stuff to get in trouble. Okay, so 0.04 meters. So now I have to figure out the path difference, delta R, which is going to be 37.8 minus 30.2, which is going to be, what, 7.6 meters. So then I look at delta R divided by lambda, which is going to be 7.6 divided by 0.04. And I get 190 on the dot. Okay? So that means this is an integer. Okay? So that is an integer. So that means we are going to have constructive interference at that spot. Okay? There's a problem in today's quiz where I ask you to compute the path difference in units of wavelengths. What I mean by that is you just compute that ratio. So you just tell me what that ratio is. Okay? Let's see. No, one thing I want to point out is that what was I going to say? It doesn't matter whether we called this source 1 and that source 2, or that source 1 and that source 2. Okay? And the reason is, if we had done this differently, suppose we had done 30.2 minus 37.8. Then we would get a delta R of negative 7.6. And then we do this ratio and we would get negative 190, which is still an integer. So you would still have constructive interference. So see how switching up the source, which is number 1 and which is number 2, it changes this ratio, but it doesn't change your conclusion about whether there's constructive or destructive interference. Okay. Another thing I want to point out is that as the observer moves around, so what if the observer moved to right here? Then these distances are going to change, and so the observer could move from a location where there's constructive interference to one where there's destructive interference, for example. Or, what if we were talking about a different wave? What if we were talking about light waves? Okay, light waves, if one type of wave has constructive interference, then that doesn't mean that another type of wave is going to have constructive interference at that location. Why? Because the speed of light is different from the speed of sound, and so that means that the lambda is going to be different for a given frequency. Okay? Even if the temperature changes, if the temperature of the air changes, that affects the speed of sound, which affects the wavelength, which affects whether it's constructive or destructive interference. Okay? At any rate, that's my lesson for today. And so I will see you in the Zoom room where we will talk about IAs if you have any questions for me. Then after we've discussed it, I will let you guys go early. Okay, see you in the Zoom.